what I want to briefly deal with is one of the work packages on cumulative impact assessment in hydropower development. It's a lot of work that we did in conjunction with Christian's group at IGB. As we are aware, there are numerous hydropower schemes across Europe. The left-hand figure indicates the major hydropower schemes that are in Europe, plotted by WWF a few years ago. And the right gives you also the number of barriers that Carlos talked about this morning from the AMBER project. And as you can see, many of the rivers that we've actually got here have got multiple schemes in these systems. The key issue about hydropower development, and one of the key issues that we tend to overlook, is what's the potential impacts of multiple dams and particularly hydropower schemes in a single catchment or a single river course. This seems to be largely missed out when people are designing hydropower schemes. What we traditionally tend to do is just look at the scheme that's being proposed or being developed and looking at the impact of it in its position in relation to its position in the catchment. We tend to look at the impacts of the barrier, the loss of connectivity, disruption to flow regimes, sediment dynamics, the loss of upstream empowerment, upstream habitat by impoundments, and the entrainment and turbine damage, all the things that's been talked about already today. The key issue here is, and here's an example for Scotland, what's the problem when you've got multiple schemes in a single impact? And this is the River system in Scotland, where there are something like 30 schemes in one catchment. What's the multiple effects of those and cumulative effects of those schemes in the one catchment? We tend to rather overlook this. The key to a lot of this also is the positioning of where these schemes are. In the left-hand system here, if the schemes are in the headwaters and really in the small streams in the headwaters, the likely impacts could be quite small. They might be just losing some of the habitat. Alternatively, when you've got schemes coming up a major river channel, you can have huge impacts as the schemes impact individually as the fish might move up and downstream. So understanding the relationships between the siting of the hydropower schemes, where they are in the catchments, where they are in relation to the river network, is a very important aspect, and this is what this work package actually looked at. Generally what we tend to use was population vulnerability analysis to do the assessments, where we're looking at the life history traits, phenology, distribution of fish species in relation to the hydropower schemes as one input, and then the potential impacts of the schemes itself, and looking at things like mortality, injury, disruption to migration, loss of habitat, and various other things, and also the role of mitigation measures to overcome some of the problems. This comes out of some of this from Ruben's previous talk, can inform some of this. What we really need is actually to look at multiple schemes. So you don't just look at the one scheme independently. We need to look at numerous schemes together to determine the cumulative impact of these schemes on all these different characteristics. And this is quite important and an aspect that we tend to rather overlook. So in this system, we've actually broken down the tools to develop this according to diadromous species and cataderous species, plus diadromous species, which we again tend to overlook, because everybody wants to concentrate on species that are moving long distances up and down the river. And we built it into a life cycle analysis. So here we've got a classic life cycle analysis of an anadrous species such as salmon. And we're looking at how the schemes can impact both the upstream movement and dispersal, and also the downstream movement and survival of offspring and juvenile offsprings, and then run it into a life cycle analysis. We can do the similar sort of thing for diadromous species, and here's an example for the River Elbe that Christian and his colleagues produced. Again, where you're looking at the fish from the starting position, moving to spawning, recruitment, and then obviously redistribution of the systems. And so looking at this aspect, we need to build in a number of components from the life cycle analyses to build the cumulative impact assessment. And we do this by looking at three main components. One is to deal with the connectivity issue. So can the fish get to their spawning habitat? Can they spawn? Can they breed, etc., etc. So we made use of Cote's dendritic connectivity index using GIS software, where you can actually plot and determine the loss of habitat and loss of connectivity to the system. And this is sort of an example that we've got down here on the right-hand side, where you've actually got different barriers that could disconnect different sections of the river or different components of the river, depending on where they are located. We currently have a Python software to help us deal with this, although that's still in testing phase at the moment, because it's proved extremely complex to work out. The other next component is barrier passability, and this is both in an upstream and downstream direction, and what proportion of fish can get upstream past each one and downstream past each one, and you then do the cumulative effect. So this is if they can get past all barriers easily, 100%, and different percentages down to lowest percentage passability, and therefore you lose your population from the system. The final one is actually looking at habitat suitability and availability and the positioning of the schemes in the system and how it could disconnect various habitats. And the three main areas that you could lose, if you have a barrier and a scheme high up the system, you could lose the headwater habitat, which may or may not be important depending on its spawning habitat, nursery habitat, etc. You've got the habitat that's lost caused by the barrier itself, the impoundment itself, which can contribute to quite a significant amount of habitat if the barriers and the impoundments are large. And the example here on the right-hand side is for Austria, where you can actually look at the impounded sections of river in Austrian schemes, which show you the potential loss of habitat for rheophilic type species. And then you've got the impacted reach between the hydropower schemes created by bypass channels and stuff. And this can be quite significant depending on the mode of operation of the scheme. What we do with all this components is actually put it together in a model and develop a cumulative output where you're putting in all the barrier distributions, river networks and connectivity, the passability systems and linking to the life cycles, and then build the CIA for both diadromous and diadromous species. And it's very important that we account for both types of species and not just one, because it is a cumulative effect on all species and fish community structure. And then we can calculate the overall cumulative impact. What this will help us do is decide where to site projects and also how to mitigate them. So you can actually put in mitigation measures to look at the impact that would have on the cumulative impact. So the tool does allow us to account for all those components. Okay, so that's my talk. Thank you very much.